In this video, we're going to learn to calculate correlation of returns. In order to do that, we have to have covariance calculation, standard deviation, expected return. We'll go through all of those different components. And we're going to start with prices. So I have prices for Apple and ExxonMobil, monthly data in 2014, and it's important that that's monthly. And I want to find the returns because I need the correlation of returns. I need the covariance of returns, not the correlation of prices. It's a slightly different concept. So in order to calculate the returns, I'm going to say my return in month 1 for Apple is equal to the natural log of the price I have right here in February, which would be 526.24 divided by the previous month of January price, 500.60. That will equal 0.0499. Okay, so very similar to that. Let's look at this return right here. That would be my return 3 for ExxonMobil. That would be the natural log of 102, the ending price in this case, 102.41, divided by the beginning price, 97.68. Now notice the ending price and the beginning price changes through time because we're going back through historical data. That's equal to 0.0473. So that's how I do each of my returns. And now let's think about what we're going to do for a measure of risk. So I want to find, at the end of the day, not only the correlation but the variance or the risk of these two companies. So how do I do that? Well, I want to see what was expected, and I'm going to define risk as deviations. So that's why I have the term here, deviations from what I expect. So in order to find what I expect, I take the average of all of these returns. I find the average is 5.87. Now importantly, that's monthly data, so that would be 5.87% per month. Well, I never talk about returns in monthly terms. I always talk about them annualized. So because I've done the natural log here, because I have those type of returns, I can multiply by 12. So 5.87 multiplied by 12 is 70.4, and that's going to be my annualized return. Likewise with ExxonMobil, the monthly return is 2.17, and the annualized return multiplied by 12 is 26.08. Okay, so let's go back to finding the risk of Apple. So to find the risk of Apple, what I'm going to do is find how much does it deviate from what I expect. So here this first month, and I'll do this in decimal form. Let me do it right here. 0.0499. Well, that's what actually happened, but I expected 5.87 because that's what happens on average every month. Right? And so the next month is 0.0198. So that was a return for that month of 1.98%. Well, that's a lot worse than what I expect to have, the 5.87%. And then this next month, 9.48%, that's better than what I expected. And then this next one, 0.0702, that's better than what I expected. These are called the deviations. So that calculation gives you, I'm sorry, not those deviations squared, gives you the deviations right here. Now I've done this in Excel, so these numbers here all go to more decimal places than what I'm showing. So if you do the math, it may not be exactly, because there will be some rounding issues, it may not be exactly what I show. So if I sum this up, that should sum to 0, because the deviations of what actually happened, what you expect, always sum to 0. The difference or the distance from average, there's just as much below average as there is above average. So how do I get rid of that 0? Well, what I want to do is I square this. I could do the absolute value and it would always make it positive, but if I square it, that would make it positive as well. So squaring that gives me all positive numbers, and this is going to be my deviation squared. This is going to be this column right there. Then I can sum that up and divide by n minus 1. Divide by n minus 1 because I don't have every price for Apple. I only have a sample of the prices for Apple. And actually, if you divide by n instead of n minus 1, it's not a big difference when we're doing this in real life. But for now, we're going to stick with the purest approach of the stats and say n minus 1 because this is a sample of the full population. It's not the population itself. So that gives me the variance. So the variance number is right here. So I need to annualize this. So I'll say the annual variance is equal to the monthly variance times 12. The monthly var times 12. And that gives me this number. Well, I want the standard deviation, and I'll tell you why I want the standard deviation, because it's going to come in handy for something like this. If I have the normal distribution, which I'm not going to draw perfectly, but just imagine that's a perfect bell curve from a normal distribution. I have here, this is mu, this is the average, so in monthly terms that's the 5.87, in annual terms of course that's the 70%. Then I have, you know, mu plus or minus 1 standard deviation. I'm in that range over here like this about 68% of the time, plus or minus 2 standard deviations about 95% of the time. The purpose of that is not to go back through the normal distribution, but to show you I'm looking for the standard deviation so I can do stuff with that later. So the standard deviation is the square root of variance. So I take the square root of both sides, and that will give me the standard deviation, and that's the annual standard deviation. That's equal to the monthly standard deviation, because the square root of monthly variance is monthly standard deviation. But it's not times 12, it's times the square root of 12. So that's how you annualize it. Okay, so what we have now is the ability to calculate the variance and annualize it, standard deviation and annualize it, and you can do it both for Apple and ExxonMobil. So how to do the covariance? Well, what I want to do for that is I'll come over here and I'll say the return for Apple minus its average return times the return for, I'll use S for return for ExxonMobil, minus its average return. This is the deviation of Apple, the deviation of Exxon. So let's look at that with real numbers. That would be equal to the 0.0499 minus 0.0587, and then multiply that by 0.0436 minus the average for Exxon, 0.0217. This is the deviation of Apple times the deviation of Exxon. And I'll do that for each one of them, so I'm not going to write each one down. I'll just do the last one so you can get the hang of it. This would be 0.0702 minus 0.0587 times this number right here minus 0.0185 and subtract 0.0217. So I take the deviations for Apple and multiply by the deviations for ExxonMobil, and what that's telling me is the relationship between the two. It says, look, Apple in this case underperformed what we expected, and Exxon overperformed. So this is a negative times a positive, that gives me a negative, and here Apple overperformed and Exxon underperformed. So again, the positive times the negative is negative, and we can see in different cases sometimes Apple beats its expectations, sometimes Exxon does. The question is, how often do they do that together or separately? What is that relationship? This is the answer to that relationship. The first time they have opposite signs, the next two they do the same thing, they both underperform, and the next time they both overperform, and the last time it's the opposite. So I sum that up, these deviations, I sum this up, and I divide by n minus 1. Now notice how much this looks exactly like covariance. In variance, I'm going to say, excuse me, notice how much this looks exactly like variance. In variance, I just squared this. I took the deviation for Apple and squared it, or multiplied it by itself, right? So when I'm doing covariance, it's the deviation of Apple times the deviation of Exxon. Same thing mathematically. I'm just taking deviations of two different stocks. Add them up, divide by n minus 1, and this is the covariance. So the way I would write this, I would say sigma subscript A for Apple, comma X for ExxonMobil. So that's the covariance, and I would say the standard deviation of Apple, sigma, well, let me do the variance of Apple. So I'm going to do the 3 lines because that's by definition. Sigma squared subscript A is the variance of A. Sigma subscript A is the standard deviation of A, and sigma A comma X is the covariance of A with X. Alright, so now that we have that terminology down, I can find the covariance. I've already found it, it's right here. What about the last thing, the correlation? Okay, so the correlation, I'm going to use the Greek letter rho, that's not a P, that's Greek letter rho, of Apple and Exxon is equal to the covariance of the two divided by their 2 standard deviations. The reason I do this is because the correlation is always between +1 and -1. If I say the correlation is equal to 1, that means they move together perfectly. All these numbers are positive, and that doesn't tell me enough, right? With covariance, I just see this 0.22. I don't really know what that means. I know that it's a positive number. I know they move together, but I don't know how well they move together. If that were negative, I would know they move in opposite directions, but I don't know how well they do that. Is that every time, or is that just part of the time that they move in opposite directions? So I can do this calculation that scales it to be between -1 and +1. So I get a sense of that number. 0.19 will tell me, well, they do move together, but they don't move together perfectly. 1 is perfect. They're the same security. -1 is perfectly opposite of each other. 0 is they're independent. So that correlation number gives me something, a sense of exactly what's going on. So that's how you do the calculation, pen and paper, and I'll show you in another video how to do it in Excel.